This is the presentation on FlowCLAS, enhancing normalizing flow-based anomaly segmentation via contrastive learning. This research was a collaborative effort between the University of Toronto and MDA Space. To start, the problem of anomaly segmentation in robotics aims to detect and localize out-of-distribution or anomalous objects that deviate from a predefined set of normal objects. This task is crucial for safety-critical robotic applications such as collision avoidance in autonomous driving and safe proximity operations in space. In this paper, we explore how to improve normalizing flows for anomaly segmentation, which currently lag behind state-of-the-art discriminative methods in highly complex dynamic scenes. Normalizing flows are a sequence of invertible mappings that transform a complex data distribution into a simple tractable-based distribution, such as the multivariate Gaussian. Through the change of variables formula, it is able to compute the exact likelihood of an input with linear time complexity. Normalizing flow-based anomaly segmentation methods are traditionally unsupervised methods, meaning they are only trained using normal, non-anomalous images. We therefore applied the outlier exposure data augmentation technique to expose your model to synthetic outlier objects from an auxiliary dataset such as the COCO dataset. The goal is to encourage low confidence for these outlier regions that were inserted while preserving inline performance from the original image. In FlowCLAS, we integrate outlier exposure into the normalized flow framework. Given an image with the inserted anomalous object, we extract features from using a pre-trained vision encoder, and then pass these features into a normalizing flow, which map them to another latent space, modeled by a multivariate Gaussian distribution. In addition to the conventional likelihood maximization of inlier samples, we also add a contrastive loss, which encourages separation between inliers and outliers in this latent space for better anomaly discrimination. Specifically, our final objective is a weighted sum of 4 losses: cross-entropy and low-VAS softmax to train for segmentation using the latent features, the negative log likelihood loss for likelihood maximization, and the contrastive loss for explicit push and pulling of these latent features. At inference, FlowCLAS follows the conventional scheme where the extracted pre-trained features are passed to the normalizing flow to get a latent map for the input image, which are then used to compute the pixel-wise anomaly score map. To further improve performance and to also enforce object-level score consistency, we employ a pre-trained class-agnostic mask generator like SAM2 to extract instance masks and then use histogram-based smoothing in each mask. FlowCLAS outperforms all existing methods on the ALU benchmark, on the area under the precision recall curve metric, and also remains competitive on the FPR95 metric. Here we compare FlowCLAS against FastFlow, a previous normalizing flow-based method from the ALU benchmark, and UNO, the state-of-the-art discriminative method for road anomaly segmentation. We can see that our method is able to localize the anomalous Mars ingenuity helicopter very well in the heat node at the top. This performance improvement is also shown in the anomaly score histogram below, where clear separation between the orange and green histograms indicate better anomaly discrimination. Next, we evaluated FlowCLAS on feature skips less than found and road anomaly validation sets for road anomaly segmentation. Our method achieved state-of-the-art performance on all metrics, even when compared to the previous state-of-the-art method, UNO, enhanced by a stronger dyno feature extractor. Similarly, our method achieves state-of-the-art performance on obstacle track of segment me if you can benchmark, and competitive performance on the anomaly track. In these two examples from feature skips, you can see that FlowCLAS outputs stronger confidence for the anomalous objects circled in red. And similarly, in these two examples from road anomaly segmentation, we can see that FlowCLAS also outputs stronger confidence for these anomalous objects circled in red. That is the end of this presentation, and thank you for listening.